Okay, that is running. And what we will take a look on today. So as mentioned, I think we are done with our messenger client. So we can start something else, but since we don't have much time, we will not be starting like a complete other project in Qt, but take a deeper look on the more low-level aspects of programming. And I wanted to show you how function hooking and code injection into other processes works. I think this is quite a useful skill to have, and it's certainly not something that is widely taught. So it should be interesting enough. We will create a new project for that. We don't need any Qt, so we'll just go for create new project for just a normal console application. Let's call it hook test because we test function hooking. Okay. And let's include a few things like Windows H. And since we have Windows H, we can show a message box even though this is a console application. So null, comma, text. Caption is, I think, the title. And here we can mb okay. So we just show us a message box, and we need to use the Unicode version of the string. So technically we are calling message box v. If you look where message box points to, it is just by the presence of this template. Usually it resolves to message box v, even though here it doesn't see that we have the Unicode specified, but we could see it here that it didn't work without the L. So without making the string a wide string. And of course, if we run it, it will just show us a message box. That's simple enough. The whole idea here is to have a nice function which we can then start to manipulate. As you see, it does what we tell it. It just says title and is a test, and then terminates. So what we want to do, what our goal is to manipulate the message box function, which gets loaded from a library in a way such that we can make it do something else than what the program as such intended it to do. So first of all, let's just put a breakpoint here. Make our disassembly a bit bigger. We could also move a few things to the side which we don't need. And the first step is to just look how this function actually works. So we have here our line. We see that there is quite a bit unnecessary code. So before we dive in, let's get rid of that. So in the debug build, the thing uses a few okay, this is fine. This is fine. Code generation. Okay, we don't want any runtime checks. The runtime library must state. We don't want any security checks. Should be somewhere option for just my code. Yeah, we don't want just my code support either. Might be enough. Let's see if the function looks cleaner. And it does. So there were some calls here which now are gone. So let's take a look to what it does. So basically what we are doing is we just have here the 4 arguments for the function. And if you have watched part 1 of the lecture last semester, you already know how the calling convention in x86 works. But since many of you were, I think, new and just joined for part 2, let's quickly recap this. On any CPU, you have such very small memory units called registers, in which you can store informations either as results of computation or by moving data to those registers from memory or from those registers to the memory. and all the operations that that a CPU performs ultimately are performed on data in register. So a CPU usually does not perform operations directly on data in memory. It needs to load them into a register to do something with it. Even though with a complex instruction set as you have in x86 CPUs, there are many instructions which directly take a memory address and a register and then already do something more complex. So usually, for example, you can have an instruction that loads data from a memory address and adds a value to it and stores the result in a register, or similar complex instructions which are made up of multiple steps. In this case here, when we look on our message box V, we see first that R9 is one of the let's start again. I lost the track a bit. So we have these registers. First of all, we would take a look on them. So you see these are all the registers that are available. Some of them have a special purpose, like the RIP register, RSP, RBP, and some of them are fully generic. RAX, RBX, RCX, and RDX are mostly just the basic general purpose registers. RSI and RDI can be used as general purpose registers, but they have some special functionality together with the RCX register if you want to implement very short loops directly in hardware. And the R8 until R15 are the additional registers that have been introduced in the x86 architecture extension. So basically you have like 8 basic registers, and then you have 8 extended registers in x86, and all these R8 through R15 registers are fully general purpose. They don't have any special function. While as mentioned, the lower 8, some of them have a bit of a special function, but can usually be also used as a general purpose register. And the way arguments are passed to a function is twofold. So first of all, the first 4 arguments which are passed, so as we have see it here in this function, are passed, if I recall correctly, RCX, RDX, R8 and R9. So if we look here from the back, we first set R9 to 0. We use XOR. The compiler often uses XOR operation to do it. If you XOR a number with itself, the resulting mathematical operation is always 0, and XOR just needs 3 bytes to be to be executed, while for example storing a value into a 32-bit register would require you to at least provide the value itself, so that would be already at least 4 bytes just for zeros. So such tricks help to make the code size smaller. Then we use the load address instruction to load the address of the string title, which just lies somewhere in our binary, to the R8 register. That should be R. And then we do the same with the other string to the RDX register. And then we again use XOR to clear the first register. So the first 4 arguments are stored in registers, and if we would call a function which has more registers, then the values for those arguments would be stored on the stack. And this not uniform way of passing arguments is done mostly for the purpose of allowing certain optimizations which the compiler can implement. There is a catch-22, so to say, here with this mechanism, namely that in some scenarios it would be beneficial to have all the arguments which have been passed to a function stored in a consecutive memory space. And for example, if you have variable argument functions, then this would be quite useful. And to allow for this to work, despite of this despite of the 4 arguments being passed in registers, this has been simply implemented such that when the function is being called and there are any additional arguments to be passed, there need to be additional space reserved after the fifth, sixth, or rather before the fifth, sixth, and seventh, and so on argument, such that the function on its own discretion can just copy the 4 arguments to this reserved space, and then it has all the values in one consecutive memory area. We see this here even explicitly, that by shifting the stack pointer by 20h, so 32, which is 4 times 8, which is the size needed to store these arguments. And generally, if the compiler optimizes, then you can, for the most part, have this space available without explicit operations to allocate it, simply by allocating a bit more space initially, and then you might be wasting a few bytes of memory, but this is not really a problem with regard to the stack space, and as mentioned, it allows you for this nice feature that you can have all the arguments in one memory area. And then of course it's up to the function whether it needs this or not, so the function can use this memory area also for other applications. It can use it as a scratch area or for some temporary data. It doesn't need to use it to copy its arguments there. Okay, so, and now of course once we have prepared all the arguments, click, did we change something? Oh yes, I changed the comment. So let's quickly rerun it. There is just a call, and then we will see where the function takes us. So we have here our 4 arguments. Wait. There is a small catch when using the debugger, namely it depending on whether the focus is in the text window or in the disassembly window, the single step button has the function that either really steps one instruction, or here it would just step one line, so that can be multiple instructions. We of course want just to step one line, and when we step in here we end up directly in the user32 DLL, so it is a Windows DLL which is used to provide a lot of interface functionality, and then we see the content of the function which does something internally. We don't at this point care that much of about what it is doing. We just care to see that it's somewhere else, and now we will want to modify it. So the first step here might be to just create some own function that can be used in place of the message box function. So we can just go to the definition of our function and copy the whole definition. This is easy enough, and we need to have the same calling convention, etc. for this to work. And let's call this my message box v. And for now we will make this function just do nothing. We just make it return 0. And obviously if we would we need this? No, we don't need that. No, it's fine. So if we would now just of course call our function, this is quite boring and not function hooking. This is just for demonstration purposes. That now we still have the same initial preparation, but we are now jumping to actually to a jump table, which we could disable if we don't want to, and then to our function, which here actually, since it's compiled in the debugger, it does everything by the book, so it copies all the 4 arguments to the memory, even though it doesn't do anything with them. So now let's start with the fancy process of actually manipulating the message box v function itself. So first thing we will do is we will get the address of the function, so void asterisk message box v. This can be as easy as just writing it like this. If you would want to manipulate a function for which you don't have a include and a library, then you could use load library and get procedure address, get proc address to get the address directly. We can demonstrate this later maybe as well. And but for now this is simple enough. Okay. Then what we also want is the address of our other function. So this one we need to get this way. We could in principle just use this directly, but it's nice to have this cassette to avoid, so that we can be a bit more flexible with it. And right, this is fixed. Let's quickly now look what the original function will be doing, or actually we can do it even simpler. So basically this variable points us already directly to the memory where the message box function lives, and we could already now start modifying it. So first of all, if we would try to modify it, so we could, for example, let's do this step by step. So first of all, I will define a small helpful helper, a union. I'll call it code from which is a union of a character, a word. So a word is 2 characters, pb, a double word, which are 4 characters, pd, and a uint64 number. It can also be referred to as a q. It can also be referred to as a keyword, pq. Okay, we have our code. And the nice thing about this helper is that it makes it really easy to write to some memory address step by step. So we have code.pbyte is equals uchar stern. Here we take our original function address. And now if we want to call already our function, we could start writing that code, but for this one we would need to know what we have to write there. So it is now quite helpful to get some means of creating machine code. So for example, there is a quite useful online disassembler. Was it this one? I think it's this one. Yep. So we can just write assembler code here, like let's say move apps x 1 2 3 4 5 6 7 8, or just move. Yeah, if move x should be what does it need? Like I need to specify what I'm moving it. Pointer to what pointer? That should work with a value. It might not like the 0x assembly. Right, x64. I didn't switch here to the 64-bit assembly. So rax is only defined as a register in 64-bit. If you want 32-bit, then you need to use rax. Then it would have worked as well. It's a bit annoying that the default is 64-bit. And what this site does is it generates for you the machine code for any given assembler instruction. I think move apps it should also understand. Yeah. So this works just fine. And of course the next thing we'd want, so what we could want here is to move some address into a register, for example rax. As you remember, rax is not used when calling, so it's so we can do with it what we want. And then of course we would want to jump to this register, so jmp should just jump to this value, and here we get the representation of how this would look directly in machine code. So we can write this down, and then we will just here use our helper to fill the code. Now a short disclaimer, when we run this will crash because the memory where MessageBox is located is read-only, but we will fix that later. I just here first wanted to put some test code in this thing. So when we look on what we got here, we have here 4 zeros. Since it's a 64-bit register, this here has 8 zeros for 4 bytes and 8 zeros in hex. And then the values, which are also front to back, so this is related to the notation, and we see that the instruction itself is only 2 byte plus the value. So here you can either write it bytewise or use the p-word to write it. And since we need to enter this as an integer number, we need to do a short reverse of the byte order. So make b8 for 8 instead of for 8b8. When this is written, it will swap those 2 bytes in the order which it does. And then for the code, we also need to get the destination. So here, right. So first of all, we need to make asterisk plus plus. So first of all, we dereference the position so that we write the memory, and then we advance by however many bytes this thing is. The same thing here. So we don't need to do any additional calculations. We just have one-liners for everything we want to add. And here, of course, we want to put our jump address. So we have our jump instruction, our not yet jump, our move rax absolute, and then we have here the target, and then of course the last thing will be the jump instruction itself, which again is just 2 bytes long, and in this case E0FF. And that would already be it. So when we now try to run it, we should just end up with the thing crashing because of a memory access violation. So we'll take a look into fixing that in a second. Let's just quickly run it to see that it crashes as expected. So here it tries to write and it cannot. And to change this, what we need to do is basically we need to ask the operating system to make this memory writable for us. There is no way for us as a program running in user space to change the page settings on a given memory page. This privilege is held by the operating system kernel, so we need to use a special function called virtual protect. It's called virtual protect because it changes the protection on virtual memory, and there we can specify the address. So of what we want to change, then we have to specify the size, so how many bytes we want to overwrite, to be able to overwrite. Technically this works with the granularity of a entire page. So even if we now would say we want to only overwrite 32 bytes, it would ideally, it would practically remove the write protection on an entire 4 kilobyte page. The reason why here we can specify a size is that ideally a program as such should have, like, let's say, an abstraction from the memory layout. So an application should not care about whether the system it runs on uses a 4 or a 16 kilobyte page size. So it just specifies the size plus the memory we want to write might lie at the boundary of 2 pages. So if we just specify how much we want to overwrite, then the operating system can look: A, does it fit in one page? B, does it overlap with a second page? And then make the pages which we want to be able to modify modifiable. And then we can, of course, we have to specify which protection we want for the page. So page. So we want the page to be executable still, otherwise when we call a function on it, it will crash. And we want it to be now read-write. Usually for security reasons, pages are either read-write or executable and readable, but execute read-write is dangerous. So what we will want to do is to undo this change later on. And for this we will store in a temporary variable the old protection flags. So however the page was configured before, we will just revert to it in a quite simple way. We just use the same function, but instead of specifying page read write, we just specify our whatever the function here returned, and then we can overwrite a temporary value. We don't care for it anymore because we want to use it. So now when we run it, our expectation is that we can put a breakpoint here that will arrive at this breakpoint once we invoke the function here, and then we'll arrive at our return 0 without anything having been done yet. So let's try this out, and now let's call this, and voila, we end up in our own detour function from which we can return, and the program terminates without any issues. We can now of course make a step-by-step step through the whole thing. So we have here again our initialization of the argument list. We have our call into the user32 DLL, which now has been modified. So let's step through it, and when we step in here, we see our move operation where we store our address in memory. Then we have our jump, and then we probably see some garbage because we didn't care for finding the proper place where to terminate our insertion. We just overrid the very beginning of the function. So here we can execute those two steps, and then again we end up in this jump table. I should disable those jump tables, that makes things confusing. And then we are in our function, and then when this function says return, we do not return to the hooked function, we return directly to from wherever the original function has been invoked. So here when we return, we are directly back in main. We don't go back again through the hooked function from which we came. And voila, then we can terminate everything. Let's quickly disable these jump tables. I think this was a linker setting. I think it's this one. Let's see. Yeah. I think the cursor was in the wrong window again. Let's click into our disassembly and then step through everything. Zack, zack. Right. So now we don't go through this jump table. The reason for this jump table is such that you could later on be able to modify to some extent the code within the debugger when you are debugging. So it's really just a debug feature, and it is not quite as useful. So it's useful to disable it if you want to do such low-level things. Okay, so now what we basically done is we have manipulated a function in a DLL which doesn't belong to us to do something we want it to do. This modification is only effective within the process in which we are right now. So even a DLL is usually considered to be something that can be shared amongst a couple processes to save on memory, on the memory footprint. The way this is implemented in Windows is it's a copy on write mechanics. So if you load the same DLL in 3 processes, each of them will ideally get the same DLL. But as soon as in one of the processes you try to write to the DLL, what will happen is for at least the one page in which you are writing, a copy of the page will be created. In your memory view for your process, this page will be swapped with your very own page to which you are allowed to write, and this way you will not be able to manipulate the DLL's behavior in other processes on the system, only in your own process. And at the same time, if a DLL is used by many processes, it will not consume memory except for the few pages which gets modified multiple times. There are also scenarios where the operating system might load a DLL fully for a second time for a given process. This happens sometimes when you load a DLL much later, or where you have specified some constraints on the usage of base addresses in your process, and then the required base address for the DLL is no longer available. So generally, when you have any code, the code expects to find certain other code fragments of itself in specified memory at specified memory addresses. This is mostly an issue with 32-bit code, because there you don't have as many options to create position independent code. in x86 you can quite easily generate a very position independent code, so that these issues don't appear, but in 42-bit they do, and they can also happen in 64-bit, especially if you have, for example, hard-coded strings like our test, or this is a test, where is it? Here, those things will be put at usually at fixed locations, and then if you load the DLL to a different location than where you wanted it to go, the offsets would not match. So what happens then is usually the operating system will so first of all, the compiler will make a list inside the DLL with all the locations of position informations, and then when the operating system loads the DLL, it can inspect the list and see, okay, if the DLL wasn't loaded to its desired base address, at all these addresses, I need to change the offsets accordingly to where I now put the DLL in. And so basically the DLL gets loaded, it gets slightly rewritten while it's being loaded, so a DLL in memory will usually not look exactly like it looked on hard disk. And then once it is loaded to a given base address, multiple processes can use it. And now of course you could have loaded a process, then loaded something into memory into the range which this DLL requires. And then if you try to load this DLL later, then the operating system sees, okay, for your particular memory layout, the DLL cannot live where it was supposed to be, or where it would be convenient, let's say it like this, where it would be convenient to reuse the existing DLL, and then it needs to fully load it just to another address. So this much to a small detour with regard to this. But in any case, if we modify the way a function behaves, we might want to still be able to use the original function. So let's say you want to modify one message box, but you want other message boxes to work normally. As it is now, we have broken the message box function entirely. It will always just detour to our own implementation, and since and we don't have a simple way to now call the original message box. So for example, we would want to filter the message boxes based on text and then show them if the text is fine, and not show them if the text contains something we don't want to show or whatever. So what we need to do now is to find out a way how we could make the message box work again when we want to end. There are two strategies to do so. One would be, of course, once we are here, what we could do is we could restore the original function, and then when it is called again, then it will work. We can quickly try this out. This is, of course, not the best way of doing things, but at least it's one of the options that we have. So we would need a variable. Let's call it ochar. MSK box backup. Let's think 32 characters should be enough. So here, before we start modifying it, we memcopy to our backup from this address 32 characters. Voila. And then what we want is simply to kind of do the reverse once we are inside our function. Of course, this needs to be slightly different, so we need to change the order here. And one thing I already see is we need to move our pointer. Actually, we could just copy it, but let's not. Let's just add it like this. So I will add a variable here. So we can, and this one I will also move. Nah, this one doesn't matter. Actually, this one we really don't need. Let's just go with using the address here directly. Right. So we are in a function here. We restore the original, and what we could now do is we could now call the original message box. Pass the arguments we got. No, could we? Could we? No, we cannot. Oh, we should be able to. Should be fine. Let's try it. Oops, I don't think we will break anything. That should be fine. because we have the same signature, it should do the right cleanup. That should work just fine. And we can, for example, change the text from test, this is a test, to bam, hacked. The downside, of course, of this approach is that okay, we have forgot a semicolon somewhere here. The downside of this approach is that it's A, not thread safe, and B, it only allows you to hook the function once, and as soon as you have some and voila, it worked. But as said, if we would show the message box again, it will not work. So the second appearance of the message box will just have the old text. Yeah. If one knows that multithreading will not be a problem, then one could of course invoke the alt function and then reapply the patch to the function again. But this obviously is not a very efficient way of doing things. And when I meant issues with multithreading, when I said issues with multithreading, what I mean is the following scenario. So if you have multiple threads running, multiple threads might call a function, the message box function at the same time, and they will be then at different offsets in the code of executing this function. And if we just rewrite the function willy-nilly like here, then what might happen is that we change the code while it's in process of being executed. So the instruction pointer for another thread will then point either to a location with a different instruction that would make sense, or even points in the middle of some other instructions. So it would basically look like there is a broken instruction at this point of execution. So ideally we do not want to use such brute force strategies to call our original function. What instead is the recommended way of doing is to create a so-called trampoline, which is just a copy of a part of the original function, but it is augmented with some additional code such that it is possible to continue the execution of the original function. So before we here modify our message box, what we will want to do is we will want to create a trampoline such that we can then successfully manipulate the message box each time it appears. So I will quickly move this here so that we have a call. Then we will jump into the unmodified function and just copy the code that is there. Zack, zack. So we are here again in our message box function. Let's just copy the whole thing. Why not? Of course, another possible approach would be just to copy the whole function, but we will see in a second into why this might not be the best thing. Right, so here we have our this we moved down. Right, so what we did here was the function to which we are redirecting the execution is called a detour function, just so you know. So what we would want to do now is we would want to allocate some virtual memory somewhere close to the original function which we want to modify, and we should think about how much of the function we want to overwrite. And I think until here should be enough. So here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 characters which we are actually only modifying, which is actually less than the 32 that we said we might want to modify. And here we have, well, I won't count them, but it looks like more than 12. So that should be enough. The rest, then for the rest we don't really care. So one more thing, actually we need to count them, because what we will need in addition to the code that we will copy out of the function will also be the address where to return to the execution of the original function. So we actually need to know where this offset here is. So 1, 2, 3, 4, 5, 6, 7, 8. It's 14. So we'll save this into a variable win64. Win64. Trampoline target. Win64 from our message box. So we cast this to a Win64 that it's no longer void, and we add to this 14. So we have this target that points then here. That's here. And yeah, we leave the rest as is. And as I already mentioned, what we also will want to do is to allocate some executable and writable memory close to the original location of our function. So let's do it with a for loop. Stern address is equals Stern. We will again here copy our address of our original function, comma, then right, and we need a variable for our trampoline. So we can create a variable here. First of all, type definition, type def int, Klammer auf, calling convention Stern, and this will be, just call it T message box v. T stands for type, but the name here is quite arbitrary. We could have anything as a name, what we want, but let's go with T message box for trampoline, and then we will here create a message box. What name do we give it? Trampoline message box v. Start with null value we start with a null as value, and here inside our for loop here we will just repeat the loop as long as this is 0. And then what would be good is to if we don't manage to allocate memory at the desired address, then we will just try a page further away. Or was it 16 pages? So that should be 1 page. And here now, of course, we want to allocate the memory. To message box. We use again a function from the operating system, virtual alloc. The function takes an address which is like we would like have some memory there, please. It might obey it or not. It will usually return something close on its own, but it also might fail, so just to be on the safe side, we run this in a loop. Again, we assume 32 bytes should be enough, and now we specify the allocation type. Memcommit and memreserve. And then again page execute read write. We can copy it from here, we already typed it down. And if it works, then the loop will break. If it doesn't work, it will just repeat with further and further away pointing addresses. Okay, so this works already nice enough. And the next step, we can use our helper here to write to our trampoline as well. Maybe we should add some comments. Function, and here we have this comment we already have, so we'll put it here. Right, so let's see what we want to put in there. I'll just delete some of this because it just takes space unnecessarily. I want to see what's on top. So we have here our code punct p word, not the double word. Right, is equals 0x 38 ec 8348 right, asterisk plus plus. So this is our sub RSP. Then we have our XOR, that will be 3 characters, which is not great because there are no 3 character data types, so we will just go with a byte and then just write it one by one. 0x45, 0x33, and 0x db. This XOR here. Rightio. And then we have here this compare instruction, which is 3 and 4 characters long. So we will use the again 3 individual bytes for the first 3 is bytes for 439 Then we will use a double word plus plus to write the rest, which is this much 0x 0003 7972 D1. Yep. And this will cause a crash, but we will see it why in a second. CMP something. Right. This we have, and now what we need is, of course, we want to jump to the remainder of our function. So we can actually just copy the code which we wrote here, because it's just the same jump. Just that as target we will specify the drum target, so that we jump in here so that the rest of the execution of the code can continue as usual. Okay, that is it. The trampoline is ready. Now we hook the function, and then our expectation is that we should be able to call our trampoline from here, just like we did before with the restored function. But as I mentioned earlier, we will run into a crash, or at least we should run into a crash. Let's put a breakpoint here. Right, let's I think I removed one of the lines. Yeah, let's add this twice so that if it would work, then we would see it doing its thing twice. So we enter here again. We prepare the arguments. We call the function. Now we jump to our special detour function. You see the rest here of the memory is filled with zeros because we haven't used it even though. And you see also it allocated a whole page and not just 32 characters. And also you see here the question marks, which means that this memory area here is not just not readable in the sense that it might be blocked from reading, but in fact there has been no physical memory assigned to this address range within our process's address space. But now let's proceed with this. So the first steps should be fine, and I think the compare instruction, yeah, should crash. As you see, it did. And now the question is why it crashed. The answer is quite simple, because what we are doing here is the way this instruction works is it uses a relative offset to address something. So this would be an example of one of the locations in a DLL file, which if the DLL is loaded not into its default base address, which the operating system then would need to patch to the new address automatically. And basically what we can do now is we can do the same thing that the operating system would need to do. We can just try to patch the location such that the value passed here to the opcode, this value here, will be correct again. So the first thing we require to do this is to know by how much our detour function, trampoline function, sorry, our trampoline function has been displaced in relation to the original function from which we have copied the code. And by the way, this is also the reason why we want to allocate memory close to it, such that we can ensure that we can have a displacement which is less than 2 gigabyte in either direction. If it would be more than that, then making a proper fix would be much more convoluted. But if it's less than this, then it's quite easy, because here we just reuse the same instructions. We really only need to change this value. If we would have a jump which is more than what we can fit into such a 32-bit value, not jump, well, a offset that is more than what we can fit here, then we would need to somehow change the whole code to address something at a much further away location. And this might be difficult because, for example, the compare operation might only want such addresses, even though in 64-bit you would expect to be able to use 64-bit addresses. The reality is that most most opcodes only take 32-bit offsets, and the code is supposed to be then just to use relative offsets. If you want to use a absolute 64-bit offset, then you need to use this move absolute function, which you can only use to store data into a register. And then of course you would need to find out which register you can modify to keep your temporary variable, and then make CMP and then here a register instead of a relative memory location. With one thing I haven't mentioned before with regard to the registers is that when you are calling a function, some of the registers, according to the specifications, are defined such that they are volatile. This means a function can change them at any point in time, and there is no expectation of when the function terminates, the register values would be set back to original. And they are registers which are defined as non-volatile, meaning that if a function modifies them before the function returns, it needs to reset those registers to their original values. And the roughly half of the registers are defined as volatile and half are defined as non-volatile. So, for example, the RAX register is something that very often, first of all, is volatile, and secondly, is not used to pass arguments, so it's really easy to change. RBX is non-volatile, and so on. So, if you want to know this in detail, you can look this up in the specification. But for our application, we'll just try to create simple code without the need for too many additional registers. So let's go back to our task at hand. We want to find out the displacement. So this will be a 64-bit number at the beginning, which we hope is smaller than 64-bit. And there, we call it just trampoline displacement. Now we cast everything to a char. We use here our trampoline function, and we subtract from it the position of the original message box. Yeah, of the original message box V. This gives us the count in numbers by how much this offset has changed, and then ideally we here just need to subtract our displacement from the value, so we don't need the zeros here. The leading zeros are meaningless. So ideally now this value should be adjusted, this value here should be adjusted such that the trampoline will execute correctly, and once this was done correctly, here we are able then to jump to the remainder of the unmodified remainder of our message box function. So let's run it, and now we enter it. Zack, zack, zack. Okay, so you already see the compare instruction was successful. Now we only have to jump to the right position in the function. Here we continue at JA and then an address somewhere inside the message box function, so we are at the right offset. Let's just run the code completely, and we get our hacked message box, and then when we repeat the whole thing, we still get our hacked message box, because now the whole code is thread safe and persistent. So now we can filter what the message box is doing. So for example, we could ask a question: if message box mb yes no, I think it was like this, title question mark. So if this is equals mb yes, no IDS, I think IDS, then return -1, or else the it's not IDS, I think it's without the comma, the underscore, yep. Right, so of course this is not a realistic use case. In reality, you would have some function that does something, and then if the function does it or doesn't do it or does it wrongly, your application might end up crashing or terminating prematurely. So in this use case here, we will just pose such a direct question, and here, just for simplicity, well, let's not go for simplicity. Let's actually do it correctly. So we will just compare the text with our other text. So if vcscmp lp text comma text is 0, so on match it returns 0, then we just return id no. We don't want it to crash, and else we will just show the message box completely unaltered. So we will not even show that it was hacked or anything. We will just let it work as it should, which already is a non-trivial test case, because here we are suppressing the execution of the message box conditionally. So now what we expect is that we will arrive here at our return 0 without any message box being shown. And then we can of course remove our detour, so voila, it worked. And if we remove our detour, so we leave the original function unmodified, oops, then we will be shown the message box and have the option to make the application crash. Do you want it to fail? Yes. And we have not arrived at the later code. So this already shows us that use case. Are there any questions? No questions? Okay, if there are no more questions, then we can proceed with some more advanced and more funny things with regard to function hooking. So first of all, a bit of additional explanation. Generally, one would not manually craft such detours, because doing this by hand the way we did it here in a way assumes that we know what function we will find, and these functions can change. So in the current version of Windows in the virtual machine, the number here is like 37972, and for example on my Windows 11 host the same number is 38052. So such a handmade trampoline would really be only useful if you know exactly which version of a given platform you are targeting. Normally when hooking functions, what is commonly used is that people use more advanced libraries which are implemented in multiple ways. Either they are kind of handcrafted in the sense that they have been designed with some rudimentary understanding of the machine code and the ability to detect such instructions and automatically create displacement offsets, but in a way that they to the largest extent expect a certain pattern to be provided within the function which is being hooked. Or they are designed such that they use a full disassembler and then they can operate with pretty much any input and generate a trampoline for pretty much any function that is provided to them. There are also scenarios where it might not be possible to hook a function reliably. For example, that would be the case when the function would be crafted in a way that some internal process within the function would make the code jump back to the very beginning of the function, or maybe not the very beginning, but jump back far enough into the function preamble that it would jump into our detour code. Such functions, if such a thing happens inside a function, the only reasonable recourse would be to just completely recreate the function at a different location, which is usually not supported by any library that I know of. But such function designs are usually quite rare. So usually, if the function is not trivial, it will have enough static initialization code at the top that it will have enough room to be modified. Another approach that can be taken is that one could, instead of modifying the function itself, try to modify the references to this function. So when you, for example, have a DLL library which you are loading, then for the DLL there is a what's the right word for that? Index dictionary. It's a table which contains the names of the functions and the relative offsets within the file. And then you can of course load such a DLL and then modify the entries in this table directly, instead of modifying the functions themselves. What is nice about this approach is of course that it is simpler in many ways, because you don't need to create a detour and you don't need to create a trampoline and so on. You just need to change an offset and then remember what was the old value to jump to. But the downside is that when a DLL would call its own function, then it would usually do this not going through this jump table, but instead it would call it directly, and then you would not have control over the control flow through that function. So it would then depend on your use case whether such a hooking method is good enough for you or not. Usually, if you want to modify a DLL of some sort which you are loading, then it should be enough to be able to change the function's behavior on the interface between the different libraries, or the library and the main process. But in special cases, you might have something where you would want to change the behavior even if the function is called internally by a certain DLL, in which case an example as shown here would already work quite nicely. Now you might wonder probably in which use case such a manipulation of underlying operating system mechanics would be useful in a realistic lab setup. So a situation which might, for example, be quite common is if you have some very old hardware. Well, the age of the hardware is not the problem, rather the age of the software for it, because on older systems you only had a couple of COM ports, and you could not like specify a COM port 25 or so. Just you could go 1 through 10 maybe, and that was it. So if you have some old software that offers you only those ports in a drop down, but you have connected the hardware to a COM port which has a higher number, then you could not address it. A simple fix would of course be to just change the port number for that specific device. But if you have multiple devices and run out of low port numbers, which might happen, so in many of the experiments I work with, we have a lot of USB devices and many of them just show up as COM ports. So it can happen that you don't have enough low COM port numbers for all software to address all of them, and what you then would do could be that you just say, okay, let's manipulate the anti-create file or anti-open file function which is used when opening a COM port, and then modify it such that when it sees, aha, a comport is being opened, because other open file, like open files on disk, etc., you would not want to manipulate. But if you want to manipulate, but if you see that it is opening COM1 or is opening anything that's a comport based on the device path, then you just substitute the string passed by the old software with your own string, which then will open COM25 or 28 or 100 and something. So that it would, for example, one of the use cases where this would be useful. It might also be useful in other situations if you, for example, would have a software that in some way misbehaves. So, for example, when you let it do something, it would always reset a certain parameter, and you would not want this to happen. So you would basically want to hook something in the communication between the software and the hardware it was made for, that will suppress or modify a part of the communication exchange. So in this case, you could, of course, if the communication is done with a comport, then you could like just have a comport connected to another comport with a null modem cable, then have your software opening one comport to this loop back, and then opening the actual comport to the device, and then looping everything through the system computer twice. But this is obviously not an elegant solution. You could use a virtual comport loopback. There is software to do that available, but that might actually not be free software, so you might need to pay for it. Or of course, if it is some other more proprietary communication mechanism, then you would not have such an easy way. So then it really would be the easiest approach to just modify, for example, the write file function to continuously analyze the stream of data coming on a handle that has been identified as belonging to a comport, and then, if needed, just modify it, whether by adding, changing, or blocking a part of the communication. Yeah, so this are just a few simple use cases where it might be useful to be able to manipulate the behavior of software for which you don't have a source code available. And obviously, the next question would be, since you don't have a source code available, how do you get your function hook into some other process? So this is what we will take a look on next. We will create a target process, something that just, in our case, again, shows a few message boxes. But we will start it, and then we'll manipulate it with our own launcher process, which then will ensure that the target process will be manipulated the way we want it before it will actually start. So add a new project. Let's again use a console application, and let's call it target process or target app. Target app, create. And here we'll again just include Windows Edge, and then we'll just copy some of our test code from here already. I will switch this back, so it's suck. Okay, and if this, then let's say message box null app failed, comma okay, and what was it? There was a definition for icons, icon exclamation mark, and icon exclamation mark. Do you want the process to fail? Question. Right, so this thing fails here, or else it works great. Alright, that needs to be a white string, and instead of icon exclamation we take icon notification, icon information. That's good enough. App is running fine, and of course when we run this, is it a startup project? Then then we will make then we'll see the question, and then we can no. and it works fine. And if we select yes, then of course it will say that it crashed. Now, of course, one thing to keep in mind is that we are looking here into the x64 scenario, so the 64-bit architecture. If you are doing things for the 32-bit architecture, which probably all your old hardware software will be written in, then things might be a bit more complicated. But I think it's for the learning purposes better to just start with something simpler, because once you know the principal mechanics behind all of that, it is reasonably easy to learn how to do the things analogously in 32-bit. So we have our target process. We now here switch to our hook test, and of course, first thing we will need to take into account is that we will want to somehow get the code into get the whole code into the other function. One option, of course, would be to write shellcode, so write the whole, not just the detour and the trampoline and everything and the message box here, but also the message box here as assembler code, or even worse, machine code, which then would need to be sent. So this is a not very handy approach. Hence, we will use a different approach. We'll create a dynamic loaded library, which we will then force load into our target process. And then this library internally can be just a normal C++ library with all the fancy things. And then when it runs, it will do whatever we need it to do, such that our target application gets modified before it gets executed. So next thing we need here, new project will be a DLL. Windows, this is not Qt. Yeah, the simple DLL should be good enough. We call it DLL. Create. Okay. So as you see, it created an empty project for us. Here, this DLL main function gets called once the DLL is loaded into a process, and it actually gets called multiple times. So when it's loaded into a process, when it's unloaded from a process, when a thread is created in the process, when a thread gets destroyed in a process. So it's actually quite well, right. So actually, this is not like a main function which is called once, but it's called multiple times. But for our application, we'll just stick to looking and doing things in the attached process function for now. And I see there's a question in the chat. Someone asks how to add this failed sound from Windows. So depends where on Windows. It's automatically shown with certain message boxes. In Qt, I think you can main. You have, I think, a Q application beep. And you have this. So let's quickly see if it's the right sound. No, it crashed. Because I guess we need to first initialize the application. So let's put it here. It makes a bling sound. Is that what you wanted in Windows itself? I am sure there is an API for that. I just don't remember. Actually, we could just see how Qt does it, since they will be not doing anything else, but just they will not be doing anything else than just calling the right Windows function somewhere deep inside. So we can go here for the disassembly view. Zack. Right, we should have the source code somewhere. Qt 6 source Qt base. Right, so we can go to some private implementation. Okay, so there's a function message beep, and you can specify even which sort of beep you want. This is nice. Let's quickly test this here. Just at the beginning. So apparently you can create a beep for any sort of message box. So this will just make a normal beep. And if we say probably not MB, okay, but there should be a stop somewhere. You can stop. That should sound like an error, but I'm not sure. It will show the hand stop icon if it would be a message box. Yeah, now it makes the different sound. So you can use this message beep with the right icon code to get the right sound on any Windows platform. Okay, but let's go back to our explanations. Right, so we have here our function. So what we can do here is, first of all, we could copy our entire code from here to there. We'll just move it. We'll create a function install hook, which will be called when the DLL gets loaded. Of course, we will not care for unloading the DLL. So if the DLL gets ever unloaded, then and the application tries to use the message box function, it will crash. But that's fine. Right. So we move the whole code here. We have here our logic to manipulate the prompt. We don't need much else. Now, of course, our hook test is empty. Our target app is done. So now, the only thing we need to do is to get somehow this DLL loaded into our target process, and there are a few ways how this can be done. So the easiest way is to use a create remote thread function, which will create it will create a thread in another process, and it takes as an argument the starting address where to create which is the entry point of the thread. And what you can do is and it will take one parameter. So what you can do is you can specify the load library function to be your entry point, and you can add you can allocate some memory inside your target process, and write there the path of the DLL you want it to load. There is a issue with this method, namely that once the thread starts, it will start also the main thread in your victim program. So if the program would try to access to call the message box early enough, then it would kind of your attack would kind of fail, because then you might do your modifications after the function has already been called. So ideally, for maximal reliability, what you would want is you would want to modify the target process in some way, such that without creating an extra thread, which would then run in parallel to your to the main thread of your target application, that you then could really redirect the execution entirely. So we will take a look on some of these methods. I mean, if you are interested, I can first show you the create remote thread method, because this is quite trivial. And then we will continue with the proper approach where we do it by modifying the target process. So are you interested in this simple approach first, or should we just start with the reliable advanced one outright? Well, since no one has any preferences. Okay, there is a preference. Start with the simple one. Okay. So the first thing, of course, which we will need to do here in our test function is in our test process, is to somehow start the target process. So let's first get our own path. So my path max path 1p max path, and there is a function get module file name v, and if we specify module as null, it will give us not the path of a loaded DLL, but the path of the exam which we are ourselves. So like this, then it will give us the whole path. So we want to remove our own file name from that. So we can use vcs chr. So this searches a string from the back for a character, for a specific character. Then we skip this by 1. We assume that it will succeed. Ideally, we would of course try to check whether we got something, but we assume it will succeed, and we just set this to 0. So at this point, we just cut off from the string our own name, and then we will create a new variable, target path, and another one DLL path. Let's call it exit path and DLL path. We fill it with our path in both cases, and then we use vcs cut to add something to the path. And here exit path, how do I call it? Target app exe, and here with the DLL path you'll have obviously our in hook.dll hook.dll.dll DLL path. Yeah, I forgot the semicolons here. Right, yo. So now let's go with starting the process. Startup info v se. We initialize this to null, and process information pi. That's all capitals. We also initialize this with 0, and then we use create process v, where we specify the exit path. Then we can specify a command line which we don't want, so null. This will just be equivalent to empty command line. Then we can specify security attributes, null. We don't care. Then security attributes for the first thread, null. We don't care either. Inherit handle is false. We don't need that. Now we can specify flags, and that's the first interesting argument after the exit path. We specify create suspended. So it will create the process, but no code will have run in the process. After creation, it will be just created and waiting for being resumed. There will be one initial thread in it, which will also be suspended. By the way, a small note about threads and suspension. So this is not something I mentioned before, but it's good to know. So when your programs are running, they have their threads which are running, and a thread can either be in a running state, in a waiting state, or in a suspended state. Running state means code from the thread is being executed. Waiting state is when the thread has been called a function like wait for a single object or sleep or something. So we have seen such states already before when we took a look on sockets. So threads might be in a waiting state, and a thread can be in a suspended state, which means that it is just not executing any code and also not waiting on anything else. And usually a thread is set as suspended or is being resumed from suspended from another thread, either in the same process or in a different process. And a interesting side note here is that there is not such a thing like a suspended state for a entire process. So an entire process is considered suspended if all its threads are suspended, and it's considered well, not suspended if at least one of its threads is currently running, since the process might want to suspend some of its own threads temporarily or something. So as long as the process can do something, it is considered non-suspended. And while there are API calls in Windows to suspend an entire process by its handle, effectively internally what it does is it just calls a suspend thread on every single thread inside the process, which is not a completely reliable method, because if the process is creating many threads and you just make a snapshot of its current threads, you might be in process of suspending them and some new threads already have been created. So the only reliable moment to know which threads are suspended and which are not is at the beginning, because then you can specify that there should be no running ones at all. But anyhow, let's continue. So specify here that the first thread in the process would be suspended, and the next argument would be for the environment. The environment is a list of strings which are useful when you are doing something in a console, but other than that are usually not needed. It's just a remnant from the good old DOS days, so to say. So we specify null, but it doesn't mean that there will be an environment, just means that the default environment from the current process will be inherited. And then we can specify the current directory. So again, this is something that often is not really needed anymore, but for certain applications it has a meaning, and we specify null, which again means it will just inherit the working directory from our current process. Then we specify a pointer to our startup info and a pointer to our process info. So startup info is what specifies details about how the process should be created. In our case, we have not specified anything. Here, as you see, we have some reserved. We have then so we could specify on which desktop, we could specify a title for the window, we could specify the position where we want the window to be shown. Although, for example, for these values to have a meaning, you would need to specify here a flag that these values have been set. So we can just not set anything, not set any flags, and it will just do the defaults. Then we have also a show window, which defines whether the window will be shown like full screen or maximized, or it will be minimized to the taskbar from the get-go. We can also specify the window that it should be hidden. Of course, the application can overrule this, but if there is no explicit implementation, it will just follow these hints. And then we could also specify here some handles for the console interaction. So if you would have an application that writes something to the console or reads something from the console, and you would want to not use a console but use another program to tell it what to do and get its output, then you could specify here pipe handles for pipes which we would first need to create, and then you could read and write to set pipes and get the data in and out from these handles. But for our use case, again, we just go with the default, so we just leave everything at 0. This structure will not be modified. The process infrastructure will be modified. It will receive a handle on the process that has been created with full access rights, a handle on the first thread in the process, which in our case will be in a suspended state, and then also the process ID and the thread ID. These informations are not that necessary. One thing to keep in mind about those two handles is that if you create a process, you need to close these two handles, otherwise you will get a resource leak. So sure, in the case of our process, which then just terminates there, it doesn't matter. But if you would have a process that runs for hours and it creates other processes using create process, then you need to take care of closing set handles explicitly, otherwise at some point your process will just crash because it will not be able to allocate any more handles. Right, so at this point we have not yet did any hacking on the whole thing, so we will add a to-do here. Checked our DLL, that's our to-do for later. But for now we will just want to try to see if we at least can create the process successfully. So we make resume thread. Then we can access the H thread here. And just for completeness, close handle, thread, and process. The thread ID and the process ID are mostly not interesting, but in principle, if you have closed the handles and kept the IDs and the process has not been yet terminated, you could reopen the handle to those resources by specifying the process ID. But for now we just do this, so now it should just start the other application. Let's put the breakpoint we have a breakpoint here. So our program here actually terminates. You see even the debugger can go away completely, and our question here is still shown, and this is our target process. There is one thing we should check whether we have. Yes, we have. So we can enable child process debugging. This might mess with some things because this functionality actually adds some own function hooks to capture, create process, and then make the process wait until the debugger is attached. But this might be. No, we should not do it. So what we also can do, instead of doing this, we can do it manually. Just putting a breakpoint here. When we run and arrive at this point, the new process has already been created. When we see here in the task manager, we see here our hook test and our target app. The target app is gray because it's suspended. We see that it threads here. There is one thread and it is suspended. It's not doing anything. So now we can go on debug, attach to process, stack. Can search by text. We can attach to our target app, and then right here we can put a breakpoint up in here that we see what is being done. Now we ended up in the internal breakpoint for the debugger for the new process. This we don't care for. Now we have this breakpoint, and now we should at some point arrive here at the breakpoint in the new process. So Visual Studio is capable of debugging multiple processes at the same time. This child process debugging is actually a third-party extension that you can install if you want this functionality, but as mentioned, if you create the processes from your code in a suspended state, like here, then you can manually attach to the child process before they are resumed to do something with them. Okay, so now let's start with our first simple use case. So for it, inject, and we do this with the method, how do we call it? Create remote thread. We just call it inject create, or just inject thread. Inject DL thread. Yeah, that's a good name. This will take a handle H process and a char underscore t asterisk DLL path. Or let's go with the same name, the path. So here we'll give it the process handle so that it can modify the process, and we'll give it our DLL path as an argument. So now inside here, first thing we need is some memory inside our target process. We use the virtual alloc x function. It's very similar to the virtual alloc test that we can specify a process name, rather a process handle. Processes don't have names, they just have IDs, process handle. And then we can specify an address where we want the memory to be allocated, which we don't care, so we just say null. It will just find us some memory somewhere, we don't care what it is, and then we specify some size. So here we could go with just max path, or we could go with what's s size, what's s len, so what's s len of our string plus 1 for the terminating character, and this multiplied with size of char. If you would want max path, you would also need to multiply it with size char. Now meet and page and read write. Meeting an e. Read write. We don't need execute because this will only contain the path to our DLL. So now we write the path there. Write process memory. Write process memory. Again, we specify our H process, comma, address, which then DLL path, and then the length to be written. So actually we should just put this into a variable, and because we need the length again. And of course, realistically, this function will allocate a whole page. So we could just have here one written that would work just fine. But why not? And last thing is we can specify a variable to receive the number of bytes which has been really written. So in case the function would kind of write some of it and then see, okay, the rest cannot be written because it's not the writable memory anymore, and it would bug out. So in this case, we could here check whether written enough, but we really don't care. Also, we allocated the right amount of memory, so it should be fine. And now what we need is the address of load library w. Load library w is a function in anti-kernel, or in our modern Windows probably anti-kernel base DLL, which is used to load DLLs into a process. It's not a super low level function, so it invokes a function or a couple functions in the NTDLL internally. But for our case, the kernel32 function is a very good target because it should be loaded into any existing Windows process, and it only takes one argument, which we can easily provide. What becomes, of course, a bit more complicated is if we would want to inject code from a 32-bit to a 64-bit process or vice versa, because there it would be much more difficult to get the right address. Here we just assume that it will have the same address as in our own process. So this is like the cheapest way of doing it. And usually it will be correct. So as said, the DLLs, as I mentioned earlier, will be loaded usually into the same address space range for all the processes in order to simplify memory management and not have to patch them each time. So unless the process for some reason would just happen to want it itself to be loaded to that address, then it will be fine. Plus, in 64-bit systems, usually the DLLs get loaded into random addresses at the first start, so the chance that one would run into a conflict is especially low, since the address space is so huge, even in comparison with the maximum amount of memory you can put into a modern computer. You have 100 million. I'm exaggerating, but you have 2 to the 64 addresses in total, and half of that is usable in user space. So it's still a couple 16 exabyte or so of memory, and realistic computers nowadays might have a couple terabyte. So there is quite 1,000 times more memory available. Memory space available than actual memory. Of course, if you have some supercomputer, then things change accordingly. But for normal use cases on normal workstations, desktops, or even servers, the memory space will not run out, and likelihood of collisions is very low. So we can afford to do these simple tricks. Anyhow, now let's create our remote thread. Create remote thread, and this thing again takes a handle to a process. Then it takes security attributes, again we don't care. Then it takes stack size, we can specify null, and we'll just take the default value. Then we need to cast to the right type. Since I'm too lazy to type, I'll just copy the right type from here, and we pass, and we specify our address, and then we can specify the first parameter to be passed to this function, which will be the address of our path. And then again we'll have creation flux null and helper thread ID that is also null. So we could receive the thread ID here, but we don't want. And we can wait here for the injection to finish. So wait for single object thread, and let's wait forever, -1. in case it never finishes. But as I said, if I recall correctly, the way this will work is as soon as this thread starts, the main thread will resume as well. We can test this simply by putting a... First of all, we put a breakpoint here, so we can hook the application. Then we will have a breakpoint here, and then we go to our DLL main and have a breakpoint here. So, better there. So now we'll create the process, we will create the thread. Here we will wait until the thread terminates, so then we are at least done with the injection. And then we will call resume on this thread, but I think this might not be needed, so let's see how well this works. Zack, now debug attach to process. We could also use sometimes there is the option reattach to process if it could recognize which process it was connected to before. But here it didn't work. Okay, and now let's start. So now we again end up here in this internal breakpoint, which we skip over, and then here we unfortunately are already directly in main. So the main thread, even though we have not resumed it, has been resumed. And if we look into the task manager, we will see that there are actually quite a few additional threads, not just the main thread and our thread, but also at least 2 more. This is the main thread, and our remote thread might not even have been created yet, so let's run it. Yeah, we don't want this to fail. Or our injection actually failed completely. This is also an option. Let's put a breakpoint here and see what happens. So first of all, we have our inject thread. We have some address to which we have written the right. Oh, I think we might not have compiled the DLL. That might be the problem. So it didn't exist, and that's why it failed. We can right click here and then go to project dependencies, and then we specify our hook test to be dependent on the other projects, so that they will need to be always compiled before our own process, our own project will be compiled. So now we will always have the DLL and the test app in the newest version built before it is started. So let's again attach to our application. Alright, we have 2. We did not terminate the last one. This one. We need to terminate this one, and this one is the new one. So it's the 1153 something something. Okay, so we are connected. We have the internal breakpoint for the debugger. Now we actually managed to arrive in the DLL first. And then here we arrive in the message box. So this worked, as you see. But, as I mentioned before, if we put a second breakpoint here, continue. Sorry, that was too fast. We need to debug, attach to process. Now, another thing to take into account is that programs being debugged sometimes behave slightly differently than they would normally, because the debugger just adds delays. So in this case it actually works in the order we want it to, but let's try not to hook anything. We just not have any breakpoints anywhere. We'll just run the code and then see whether it is reliable or not. Okay, so now it seems to be reliable. We can add a delay here, say 1 second, and see if it will remain reliable. Okay, it is. This is nice. Sometimes this fails for timing reasons, so that it does not properly work with the order of operations. So sometimes, as mentioned, it happens that this will just running this way. So we could actually test this also in a different way. We can just remove the resume call and see whether it will actually start the application or whether it will terminate. Actually it didn't terminate, so it is still waiting. Okay, so this works actually quite fine. Anyhow, so this is the simple way of injecting things into the into a process. We are creating the remote thread, and now it actually works okay without just with waiting for the remote thread. Sometimes, as mentioned, this might fail if the thread internally gets resumed prematurely. But since this works fine, we will just leave it as is, and now we can take a look into the more advanced method of injecting code. Let's see which one would be interesting, because there are a few things we can do. So one thing what we can do is we can hijack the thread itself. So this means that the thread which is being executed, the main thread will work differently, but we only have 45 minutes, so we maybe keep this for the next part. And let's see what else we could try. We could try a to QA. This is actually a nice trick. We can try that. So this will, however, definitely need a long enough delay here, because it needs the thing to actually run already. Right, so let's disable this code injection, add some delay here. Sleep X, let's say we wait for a second or so before we do something. True. And now we will create a different function, void inject inject user APC. This should work. Also, we will pass to it the same arguments. Yeah. And we will also need the thread, so we could actually simplify the things by just passing to it the whole structure here, first information. So and we of course don't want to close the handles yet. We want to resume it, however, because it needs to be run. Well, does it need to run? Actually, it should be doable even without it running. First, let's try the simple way, and then we try the potentially more complex way. Of course, here we specify the path. And what we will want to do here is we will want to queue a user asynchronic procedure call to the thread directly, such that it will execute some code before it executes its own code. So here we can just copy something from the top. Actually, we can copy more. We can copy this as well, because those we will require. Okay. And address comes from PI. So we will again use the load library function, just that the way we invoke it will be different, namely sorry, that needs an error, namely such that we will not use the an own thread for it, but we will use one of the threads inside the process, namely the first thread which has been already created. We should have, I think, all the permissions on the thread, so this should work out fine. You will see okay is equals q user APC. Then we need to specify a pointer. Again, then it needs to have the right type. We again use the load library function. Then we specify the thread handle this time, and finally we specified the address and that should already work. Let's try it out. The type is wrong, so we need to cast the type first onto Oolong pointer. Okay, run. And it worked as well. So we could also see if it will work without any delays. It actually should, I think. No, it might not, but it did. And of course, if we remove the hook, then it will show us the question. Suck. So the way this approach here works is it queues a asynchronous procedure call to the main thread, to the one thread which already has been created, and when the thread exits from a alertable state, then the asynchronous procedure call will be executed. And for example, a steep X with the alertable argument set to true is one of these alertable states. We could now try to find out from where actually our procedure was invoked, just by setting a breakpoint here and then connecting to the thread being debugged. So we put a breakpoint here again. Right, one thing that we should test before is whether we can actually do this in the different order, because this should in principle inject the code much earlier, but and it works. So we put a breakpoint here and let's run. Suck. Okay, debug, attach to process, target app, attach. Okay, now we again end up in this breakpoint from the debugger, and then we end up here. So we see that somewhere from the C runtime somewhere from here. So technically this DLL main, and that is still not the right point. What do we call it? Here we have library X. Yeah. So from this will be at a very early stage of the process creation where we actually get our load library XV call injected into the process, and then of course from here on out, the things at the top here is just the procedure of loading the DLL. So LDR initialize trunk is where a process starts its life. Then we have some internal function, another internal function, and apparently at an early stage the NTDLL is using the NT-test alert function to check whether they are actually some APC skewed, and if they are executed. So this actually is a quite reliable method, more reliable than the create remote thread method that I showed first. And it is not, by the way, the complicated method which we will take a look in, I think, next time, since we are already running out of time today. So we will look onto hijacking the thread manually without using asynchronous procedure calls during the next lecture. And we will also try to not use this the known address of load library v, but we will try to either inject some code ourselves, some handmade code to call then load library v, let's say manually in quotation marks, and this should allow us ideally to make a even more generic approach. So ideally what you would want from a really reliable code is to be only reliant on the ntdll.dll and on no other DLLs, while the kernel 32 DLL and its submodules like the kernel base and so on can be expected in pretty much any process. Some processes which, if they are made particularly low level by the author, might not use them. Hence, it is quite useful to be able to write some code which can work even if kernel 32 is not loaded into a process. Another thing that might be is that you might want to take control of the process creation in the ntdll before even the process's own internal code starts execution. So also in such a scenario, it would be useful to use this more advanced hooking procedure. So during the next lecture, we will first try to just change the thread context to a piece of shellcode which we will have made by hand, and then it will call the load library function for us. First with a simple shellcode that uses load library, then we can advance this shellcode to use the load DLL function from ntdll, and later we can also try to inject some code by rewriting portions of the application which we are modifying. So one thing is we could overwrite the entry point of the application, so the main function, kind of like we did with the hook for message box at the beginning of the hour. So there we know that it will only be called once, so we just need a detour, and from the detour we can restore the backup, and then after we done our thing we can run it normally. So this is one thing we'll try, and the other thing what we will try is to hook one of the ntdll DLL internal functions, which will then invoke our shellcode long before even the C runtime gets initialized. Are there any questions? Okay, so if there are no questions, then I think this is a good point to stop for today. I will upload the lecture and the test code samples to the Moodle, and during the next lecture, which is the last lecture this semester, we will then take a look on this more advanced thingies, and that's that. So if this is already the start for the weekend for you, then have a nice weekend. If not, then have a nice Friday, and we will see each other next week. Bye bye.